Fluid mechanics class, boundary layer boundary layer theory. Hydraulics study the phenomenon that can be observed but not proved. Vice versa for hydrodynamics, but not in all the cases. These are the arrows. This is laminar boundary, this is transition, this is turbulent, laminar, transition, turbulent, then laminar sublayer, boundary layer on a thin plate. Laminar implies parabolic, turbulent implies logarithmic, transition implies parabolic. Then these are the arrows of u naught. This is laminar, this is u is equal to 0, this one is leading edge, this is transition, this is turbulent, this is u is equal to u naught, this is u approximately equal to u naught, this is u is equal to 0.99 u naught, this is boundary layer thickness, this is laminar sublayer, this is boundary layer on a thin plate, this is trailing edge, this is parabolic, this is parabolic, these are two arrows, this is logarithmic, this is u is equal to 0.99 u naught. Then boundary layer thickness ratio, laminar boundary layer where u is equal to 0.99 u naught, where only u is equal to 0.99 u naught. Re is equal to rho Vx by mu. The Re in case of laminar flow is equal to 3 into 10 raised to power 5, where Re is less than or equal to 3 into 10 raised to power 5 implies laminar boundary layer 3 into 10 raised to power 5 less than Re less than or equal to 5.5 into 10 raised to power 5 implies transition. 5.5 into 10 raised to power 5 is less than Re implies turbulent boundary layer, or Re greater than 5.5 into 10 raised to power 5 implies turbulent boundary layer. Du by dy is equal to 0 implies maximum velocity implies 3 stream velocity boundary layer. du naught by dy is equal to 0, then these are the arrows, this is u naught, then this is du naught by dy is equal to 0, du naught by dy not equal to 0, u is equal to u naught, du by dy not equal to 0, then these are the arrows, du by dy not equal to 0, u is equal to u naught, these are the arrows, these are the arrows. This is for laminar, this is maybe transition, this is for turbulent, then this is delta, then this is du by dy not equal to 0. Greater thickness in case of greater kinematic viscosity. Boundary layer parameters: delta u dy y b, these are the arrows. Area of element is equal to b into dy, since b is width of the plate. Mass flow rate through this strip is equal to rho into flow velocity into area of the strip is equal to rho into u into b dy. Boundary layer thickness, this is u, this is delta, this is u naught minus u, this is dy, this is y. Mass flow rate through a strip is equal to rho into u into b dy. Mass flow rate without the plate is equal to rho into u naught into b dy. Loss in mass is equal to rho into u naught into b dy minus rho into u into b dy. Total loss is equal to from 0 to delta rho into u naught minus u into b dy. Displacement thickness can be defined as distance by which the boundary would have to displace outwards, so that the total actual discharge would be same as that of ideal fluid past the displaced boundary. Flow in displaced boundary is equal to rho into u naught into b into delta star is equal to from 0 to delta rho into u naught minus u into b dy. Then delta star is equal to u naught from integration from 0 to delta 1 minus u over u naught into dy. Physically, displacement thickness is the distance by which the free stream is displaced by the displacement of a boundary layer. Fluid mechanics, momentum thickness, displacement thickness, momentum is equal to mass into velocity, then y, then delta y, then u, then u naught minus u, equivalent. This is equal at some line. This is u naught. This is delta. This is u is equal to 0.99 u naught. Loss in mass flow rate is equal to rho into u naught minus u into b dy. Loss in momentum is equal to rho into u naught minus u into b dy into u. Total loss in momentum is equal to from integration from 0 to delta rho into u naught minus u into b dy. Thickness of the flow at the free stream velocity and having momentum flux is equal to deficiency of momentum flux in the region of the boundary layer. Note here, thickness of the flow at the free stream velocity and having momentum flux is equal to deficiency of the momentum flux in the region of a boundary layer. Assume momentum thickness is equal to theta. Momentum flux through thickness theta is equal to momentum mass flow rate through theta into velocity is equal to rho into theta into b into u naught is equal to theta into rho into b u naught square. Dose in momentum flux is equal to flux through theta, which implies rho into theta into b into u naught square is equal to integration from 0 to delta rho into u naught minus u into b dy, implies theta is equal to integration from 0 to delta u by u naught into 1 minus u by u naught into dy. Momentum thickness defined as a distance from the actual boundary surface such that the momentum flux corresponding to the main stream velocity u naught through this distance theta is equal to deficiency or loss in momentum due to boundary layer formation. Note here, momentum thickness is defined as a distance from the actual boundary surface such that the momentum flux corresponding to the main stream velocity u naught through this distance theta is equal to deficiency or loss in the momentum due to boundary layer formation. Kinetic energy thickness for elementary strip, mass of fluid is equal to rho into u into b dy. Kinetic energy of fluid is equal to half into mass into velocity square is equal to half rho into u into b dy into u square. Kinetic energy in the absence of boundary layer is equal to half rho into u into b dy into u naught square. Loss in kinetic energy is equal to half rho into u into b dy into u naught square minus u square. Total loss in kinetic energy is equal to half into integration from 0 to delta rho into u into b into u naught square minus u square into dy. Assuming kinetic energy thickness delta E, kinetic energy through distance delta E is equal to half rho into b delta E into u naught square, implies delta E is equal to integration from 0 to delta u by u naught into 1 minus u by u naught whole square into dy. Energy thickness can be defined as the distance from the actual boundary surface such that the energy flux corresponding to the mainstream velocity through this distance delta E is equal to deficiency or loss of energy due to formation of boundary layer. Shape factor H is equal to delta star by theta. 1 u by u naught is equal to 2 into y by delta minus y by delta whole square. Then second, u by u naught is equal to y by delta whole raised to power 1 by 7. Determine displacement and momentum thickness, also energy thickness and shift factor for the falling velocity profile depend on the flat plate. This is u by u naught is equal to y by delta whole ratio 1/7 determine displacement and momentum thickness. Also energy thickness and shear factor for the following velocity profile developed on the flat plate, fat plate or flat plate. Fluid mechanics. Free stream is that stream which is not in contact with solid. When it is in contact with solid surface, velocity is zero at the wall, and as it moves away from the wall, the velocity increases. At one point, u is equal to 0.99 u infinity. Join the points of 0.99 u infinity from the boundary layer y. Then this is non-relative motion du by dy is equal to 0. This one is the curve. This is boundary layer. Relative velocity adjust du by dy not equal to 0. This is relative velocity adjust du by dy not equal to 0. Fluid mechanics boundary layer. This one is the curve. This is the line. These are the points. No relative motion du by dy is equal to 0. 0 is equal to 0.99 u infinity. Relative motion du by dy not equal to 0. U is equal to 0. No slip condition. Boundary layer is a region in the flow field inside which fluid flows with a higher relative velocity. A layer inside which a relative motion between a fluid particle may adjust. Du by dy is equal to rate of shear strain. Shear stress tau is equal to mu into du by dy. This is Newton's law of viscosity. For the region inside the boundary layer BL, tau not equal to 0. Pity. If the fluid flowing over the solid surface is incompressible, then 0 implies spin. This is ideal fluid flow. This is outside the boundary layer flow is irrotation, which implies potential flow. Tau is equal to ohm is equal to 0 is equal to velocity. Inside the boundary layer, the flow is rotational. W is equal to 0. M naught u infinity y free stream. Boundary layer thickness is equal to Fi. This is x. This is mass inside the boundary layer. This is leading edge. X is equal to 0. This is u is equal to 0. This is a delta y. U is equal to 0.99 u infinity. This one is the trailing edge. This one is the x. This is delta is equal to fx. Then this is leading edge. This is laminar flow. This is x. This is transition zone. This is turbulent flow. RECR is equal to 5 into 10 ratio of 5. R is equal to rho u infinity L by mu. L is equal to L, then length of the plate along the direction of flow. Displacement thickness delta star, momentum thickness theta, energy thickness delta double star. This is kinetic energy. This is y. This is delta star. This is 1. This is 2. This is y. This is z. Y z. M1 dot not equal to M2 dot. M1 dot less than M2 dot. Then this is x1. This is 2. This is x2. X1 less than x2. Displacement thickness delta star. Distance measured perpendicular to the solid boundary by which the solid boundary must be displaced to compensate reduction in mass flow rate. Displacement thickness delta star. Distance measured perpendicular to the solid boundary by which the solid boundary must be displaced to the compensate reduction in a mass flow rate. Momentum thickness theta. The distance measured perpendicular to the solid boundary by which the solid boundary must be displaced in order to compensate change in momentum or reduction. Energy thickness delta double star. The distance measured perpendicular to the solid boundary by which the solid boundary should be displaced in order to compensate a reduction in kinetic energy. Note here, this is u infinity, this is y, this is delta. No, this is rho. This is rho, bro, my sisters. This is rho. This one is the line. This is the curve. This is the delta into a. This is y. Then this is 0.99 u infinity. Then m dot is equal to rho into a into u infinity. Then u infinity arrows. Then x is equal to 0. Then x. Then length L. Then y. Then dy. Then u delta b. U is equal to velocity of fluid through element. Dy b. dA is equal to body area of flow in the element. when there is a boundary layer, mass flow rate dm is equal to rho into dA into mu u, dm dot is equal to rho into b dy into u. If there is no boundary layer, the entire flow will take place at uniform velocity u infinity. dm2 is equal to rho into dA into u infinity. If there is no boundary layer, the entire flow will take place at uniform velocity u infinity. dm2 is equal to rho into dA into u infinity. dm2 dot is equal to rho into dA into u infinity. u infinity greater than u, dm2 dot greater than dm1 dot. Reduction in mass flow rate for the element is equal to dm2 dot minus dm1 dot is equal to rho b into dy into u infinity minus u. Total reduction in mass flow rate is equal to integration from 0 to delta rho into b dy into u infinity minus u delta star. Then this is u infinity, this is b, this is a is equal to delta star into b. Mass flow rate or compensation for mass flow rate is equal to rho into delta star into b into u infinity. Therefore rho into delta star into b into u infinity is equal to integration from 0 to delta rho into b dy into u infinity minus u delta star is equal to 1 by u infinity integration from 0 to delta u infinity minus u into dy. Then delta star implies delta star is equal to integration from 0 to delta 1 minus u by u infinity into dy. Then this is u infinity. This one is not here, this one is leading edge. This is x is equal to 0. This is x, this is length L, this is x. Delta is equal to thickness of the boundary layer. Then y, then u, then dy, then delta, then x, then y, then b. Momentum of the element when there is a boundary layer is equal to dp1 is equal to rho into dA into u implies dp1 is equal to rho into b dy into u square. Then this is dy, this is b, this is dA is equal to b into dy. Area of flow of the element where there is no boundary layer, dp2 is equal to rho into dA into u infinity. Where there is no boundary layer, dp2 is equal to rho into dA into u infinity. Where there is no boundary layer, dp2 is equal to rho into dA into u infinity. Reduction in momentum of the element is equal to rho into b dy into u infinity minus rho into b dy into u square is equal to integration from 0 to delta rho into b dy into u infinity minus u square. A is equal to theta into b. Then this is u infinity, this is u infinite, then this is theta. Momentum is equal to rho into theta into b into u infinity. Then this is mass. Compensation in the momentum is equal to rho into theta into b into u infinity square is equal to integration from 0 to delta rho into b into dy into u infinity minus u square. Then theta is equal to 1 by u infinity square integration from 0 to delta u infinity minus u square into dy. Then theta is equal to integration from 0 to delta u by u infinity minus u by u infinity whole square into dy. Then theta is equal to integration from 0 to delta u by u infinity 1 minus u by u infinity into dy. Third kinetic energy of the element where there is a boundary layer is equal to dke1 is equal to half dm into u square is equal to half rho into b dy into u square implies dke1 is equal to half rho b dy into u cube. When there is no boundary layer, dke2 is equal to half dm into u infinity square dke2 then implies dke2 is equal to half rho into b dy into u infinity square. Reduction in kinetic energy is equal to dke2 by dke1 is equal to half rho into b dy into u infinity square minus u cube. Total reduction in kinetic energy is equal to integration from 0 to delta half rho into b dy into u infinity square minus u cube. Then these are the arrows. This is u infinity, then delta double star, then b. The compensation for changing kinetic energy is equal to half rho into a into u infinity square is equal to half rho into b into delta double star into u infinity. Therefore half rho into b into delta double star into u infinity is equal to integration from 0 to delta half rho into b dy into u infinity square and u. Then delta double star is equal to half u infinity is equal to is equal to 1 over u infinity cube integration from 0 to delta u into u infinity square minus u cube into dy implies delta double star is equal to integration from 0 to delta u by u infinity minus u by u infinity whole cube into dy. Then implies delta double star is equal to integration from 0 to delta u by u infinity into 1 minus u by u infinity whole square into dy.